acid is sour. It's always sour. And that's, I mean, they are sour beers. So they can be extremely sour and puckering. I love them like I love my IPAs. I mean, it needs to be sour. I like a bitter IPA and I like a sour beer. I want to look like that woman when I drink it. A lot of people don't like it like that. That's their business. But the first flavor that comes to mind when we talk about sour beers is sour. And I think it's the most, it's the easiest one to just talk about how it happens and why it happens. So you all are going to get a bit biochemistry.
Whoa!
About time. We're going to follow the electrons through.
Yes, all the way. Okay, so literally very easy. You guys know about the lactic acid bacteria. They make lactic acid. So that's the thing that's going to sour the beer for you. What's interesting about it is like most organisms and most yeast can actually make lactic acid as well. They, on a genetic level, just choose not to, and they rather make ethanol. But these guys, they make lactic acid. And the reason they do it is not for shits and giggles. They do it so that they can get energy. So they're doing it to live. They're taking those sweet, sweet sugars that you've created in your wort. They put it through a process called glycolysis. And they're getting some tokens. Those ATPs you see at the top, just think of them as energy tokens. You should be fairly well versed with tokens, using them the entire day. So you got money, which is sugar, and you got tokens for that, and you can spend it on stuff like beer. Well, the bacteria can go and they can spend it on stuff like growing and building stuff and living. So it's basically, I mean, you've been doing glycolysis the entire day anyway. your own little tokens. It's not a difficult thing. It takes those sugars, it turns them into pyruvate. Like I said, most living organisms can do it. You can do it as well. You know when you exercise and your muscles run out of oxygen because you're like really drinking hard that day. The next day you're drinking until it's sore. That's all that lactic acid buildup that you've got in your muscles. So you can do it as well. But these guys, these lactic acid bacteria, they specialize in it. So they take glucose, turn it into pyruvate, take it all the way to lactate and lactic acid. As it happens, I mean, Josh showed you some very interesting graphs and everything. It increases in solution, it drops the pH, and you get this nice sour in your beers. Interestingly enough, like I said, it's very similar to what yeast is doing. You can see it's basically the same picture. We've got sugars, we've got our tokens, those sugars are going to pyruvate, and then rather than making the lactic acid, yeast will go, or some yeasts will go, and they'll make ethanol for you from that. Before they make the ethanol, they'll make this lovely compound over here. They say aldehyde, that a lot of you might or might not know. If you taste your beer, you get that green apples in your beer.
Yep.
That's that acetaldehyde, and we usually couple it to beer that's not been, or that's still a bit young or a bit green, and that's just the reason for that. It hasn't had enough time to convert all of this acetaldehyde to ethanol. So now we've probably seen that as well. And what's very interesting about this process for me as well is usually if there's no oxygen, organisms would want to do this and this. But we've got these specialized yeasts that you know and love very well. Our old friend, the Saccharomyces cerevisiae, and they are what is referred to as crabtree positive yeast. So it has nothing to do with the crabs. I see you, Albie. It just means that they're a bit weird. So rather, when there's oxygen available, like I said, we'll go and we'll take those sugars, and we want maximum bang for our buck. So we're going to invest all of those sugars to get as much tokens as possible. Now think about it. If Megan came and she said, listen here, you can have one of two things. You're going to give us 250 rand, I'm going to give you 2 tokens. Or you're going to give me 250 rand, I'm going to give you 36 tokens. Which one would you take?
2.
Most of us would take the more tokens. The yeast that we love, they kind of go, we're going to go half and half.
Yeah.
Like, I'm going to take some of Megan's deal from the one end, but I'm also going to take some of this other deal where I'm going to be getting less tokens out. And Jock also mentioned that today, where he said this yeast, what it does is it makes alcohol because it kind of limits the environment it's growing in. It's producing ethanol, and a lot of other organisms living in there is going to die. So it's basically selecting so that it can do the best and it can make more money in future. It's actually a very clever little investor. The other weird thing is, what I've just told you is probably not even true. We don't know. Researching this, I was very surprised to find out it's a very nice hypothesis, and at this point it's one of the hypotheses that makes the most sense to us, but we're not really sure. Why would an organism take less money? Like, I want the most money. So I read a paper while studying for this talk that I have to give you, where the one people went, what's happening if there's a lot of sugar and the cells are making all that big bucks, basically they're getting too much money and they're partying too hard and they're going to start dying. They literally get too hot because of all of the little cellular processes that might happen during all of this fermentation. So they're going to invest some of their money in this pathway and they're going to invest some of the money in the other pathway, and by that way they're not basically overheating and dying.
That's like going to the gym on the way to the bar.
Yes.
Bruce said it's perfect. He's going to the gym first.
Once again, a theory. We don't know. This is what we're thinking is happening, but it's just interesting. What I want you to see is the fact.
The bar.
Is that the Pasteur effect? This is the Crabtree effect?
No, I mean, this is Crabtree. Pasteur effect is basically when they just do this when there's no oxygen.
Crabtree level of sugar.
Crabtree is there's oxygen, but it's still going to do this. The other one is this, they decide to do this to limit themselves a bit, so to not have too much thermodynamic heat being produced by all the enzymatic reactions. Okay, but that's the ethanol. Like I said, I just wanted you to see very similar pathways. We're investing glucose money, we're getting energy, and that's why they do it. They don't do it for fun. I know you drink it for fun, but they do it actually to survive. So that's our one acid, our lactic acid. The other acid that we get in sour beers a lot is our acetic acid, so our vinegar. We had a couple of very nice beers today that had a very nice vinegary taste in it. And what's interesting about that bacteria, the acetic acid bacteria, and there's some yeast like Brettanomyces that also make acetic acid, is they can only do this when there's oxygen present. So our acetic, can I tell them about our acetobacter culture? Thank you. So we actually got our acetobacter culture from a commercially available yeast package that we actually bought that was contaminated by this. Not Lallemand, I just want to stress that. It wasn't
Was it Anchor?
We'll get a lot of it in Anchor, but also not. It would surprise you. It's a big company, but it's not Lallemand.
Was it a Safra?
No.
Was it a Turkish company?
And most of the brewing yeast is contaminated with this, but it's not an issue if there's no oxygen in your beer. I mean, or at the end of fermentation, and if you bottle it and everything, it's going to be fine. It's not going to produce this. In some cases, like sour beers, we want that vinegar in our lambics and our Flanders and everything and that, and that's where barrel aging becomes very nice, because barrel aging is going to selectively let a small amount of oxygen through microoxidation come into your beer. It's going to let this reaction happen slowly over time, and it's also going to keep that grape nice and healthy so that it can actually live longer and making some of the other nice flavors that I'm going to talk to you a bit about. Okay, so we've spoken about two acids, our lactic acid, our acetic acid. I've told you about the ethanol. And just here you can see, but those are the acids that we know, that we think about. I'm sorry.
I can see acetic
Have more beer.
Have beer. I'll show you afterwards.
Beer go.
Or I'll recite.
Have beer.
Here at the top is acetic and lactic. Like I said, we've just spoken about them. This is butyric. That some of you that's a nice way to get into your beer. Clostridium can introduce that, and some other bacteria can also bring it. Down here are some acids that you can get from Saccharomyces and Brett that they do during fatty acid production. I've split them because on this side you can also get acids from your woods, vanillic acid, stearic acid. You can get it from your barley and your wheat. Most of you know ferulic acid, very nice in your lices. You can get it from other bacteria. So there's a lot of acids actually in these beers. being produced and coming from various sources when we're talking about sour beer. So it's not just lactic, and it's not just our acetic. But sour beers aren't just sour. They're also bready, like I said. We talk about flavors and aromas like barnyard and baby diaper.
Yep.
We talk about woody and oaky and vanilla and goat, yes. And then fruity as well. That's a big one that comes through in a lot of these beers. And these things aren't acids, but they're in the sour beers. So where do they come from? And this is basically an area of, I feel, beer that's very poorly understood, and that's usually poorly described as well when we talk about beers, and this is the esters. Mostly when we talk about esters, people go, oh, okay, it's a British ale, it's kind of fruity. You know? That's where it stops. Oh, esters, yeah, it's fruity. But esters are a lot more, and they're actually ridiculously important. And knowing where they come from and what they do and how they do it might help you if you're thinking more about your sour beers, how you're going to age them, where you're going to age them, why you want to age them, and what strains you want to put in them, what malts have to go into them as well. So, in a nutshell, basically, that's what an ester looks like. I'm not going to go into depth. We've got a carbon of the double bond oxygen, another oxygen, and some side chains. Don't worry about it too much. They are, let's firstly go back quickly. You should actually kind of worry about esters because they're ridiculously important. They form part of your cellular membranes and also the backbone of your DNA. So they are ridiculously important. But the ones, yes, don't worry about your DNA. The ones we care about are these low molecular weight esters. It's just like short little chains of esters. And we get them by basically combining an acid with an alcohol. So which beers have a lot of acids and alcohols in them? Belgians! Well, I've tasted some soury Belgians in my time. But sour beers, so they're a perfect little playground for the productions of esters, but we never really think about esters when we think about our sour beers. So if you didn't see the previous one, you're definitely not going to find this one.
Oh my lord! Paul, what's going on there?
We'll make the slides available through the Facebook group or the WhatsApp.
We'll make it special, you can have it.
Basically, this side we've seen, this is our acids and where they came from. We know where some of the acids come from. Like I said, some of the other ones come from the woods and the barleys and whatever you've been using. We want to combine it with this column, which is our alcohol. And our alcohols, we know where ethanol at least comes from. Yeah, I showed you that's from the east. So if we combine some of these acids with some of the ethanols, we get our esters. And we can dramatically change, or not us. Some of the flavors and aromas will dramatically change through this reaction over time or due to the presence of our organism. So we can go from something like acetic acid to something like ethyl acetate, which is also not great because that's nail polish remover mostly.
Horrible.
In small doses, it can, or at low levels, it can give you a pear-like aroma. So it's not always horrible. Our lactic acid, which doesn't really smell like anything, like lactic smells like sour. If that's its ester, ethyl lactate, then becomes a fruity or a sweetish cream smell that you get. So the fruit that you smell in your sour beers is usually not the sour, but the ester that came from that. The butyric that we spoke about, the nasty one that smells like vomit, if you get the ester, ethyl butyrate of that, that's pineapple. So I don't know if you've smelled a very old bread culture, like it has this really nice tangy pineapple smell. That's the horrible thing, being esterified to something nice. And the list goes on. We get all of these weird pineapple, sour cream, apple, burnt and smoky. These things from the barrel turn into our tobacco and fig and cinnamon and spicy and woody. Our other things coming from fatty acids turn into raspberry and fruity and berry and kiwi and pineapple. So all of those acids and everything with the alcohols that we have finally combine over time in these sour beers because it's the perfect little environment for this to happen into these nice flavors and aromas that we get in the lambics, those 20-year-old lambics and the Flanders and the oak grains, yes.
How do you ensure the nice flavors? Time.
Yeah. Time and luck. Yeah. Make sure, I feel with this, make sure the components are there. And if you give it time and a bit of love, if you're lucky, yes. Like I wouldn't say brew to get butyric in your beers. If you do, wait a very long time.
But what the Belgians do is they blend, they actually blend beers to get the right stuff. So they'll have 20 barrels, and the guy will pick percentages of different barrels to make a
Weight to.
That's So it's luck and time and blending.
I mean, it's difficult beers. I mean, the lambics and stuff, there's a reason you very rarely get a lambic in a competition, or all Flanders red. They take a long time and they're ridiculously difficult to get nice. But if you get a nice one, I mean, it's magic. Yes.
So to touch on your point that you said, like, don't particularly aim to brew butyric in your beers, because you need to keep in mind that pH is a huge driving factor. It's a reducing environment which aids this type of esterification occurring. So you can't aim for butyric acid in a pH 5.5 beer. You've got to do it in a 3.4 beer, because you have enough protons to be able to reduce the butyric to become the ester that you want it to be. So what you've been doing
I think also I'm running out of time. I'm running out of time.
That looks like a heavy metal album.
So, yes. So, I've mentioned aerobic respiration to you. I told you you can get a lot of money for your glucose if there's oxygen, or you can get a little bit of money. This is how the bacteria and yeast get a lot of money. So you start with your glucose and you go through glycolysis. This pyruvate at the end turns into this acetyl-CoA, goes into your Krebs cycle, goes to your electron chain. And you can see all of these little places is where the cell's getting those tokens that it can spend at the bacteria store. You see all the So don't worry, I don't. What?
Sorry, joining us. Excuse me.
What I want you to see, because we're talking about esters, and this is applicable to sour beers, but it's also applicable to your normal beers.
Yeah.
This component down here, the acetyl-CoA, becomes very important. So that's why I'm bringing it in here. All of the esters that you get don't come from acids mixing with the ethanols to give you the final ester of things. And lots of the esters in normal fermentation and in sour beer fermentation comes from this little guy down here. So under normal circumstances, like I said, glycolysis, you give it the sugar, it wants to make the money, gets to the pyruvates. Some of this pyruvate is going to get turned into ethanol, some of it is going to go over here, and once it's over here, three things can happen to it. One is it can do that, it can get the money, so it can get the energy tokens.
It's hard.
The second thing it can do is it can become part of fatty acid biosynthesis. You can make fatty acids, and this is very important. So if you ever wondered, why do I aerate my worts? This is one of the reasons. This reaction needs oxygen. So you need oxygen in there so that the healthy cells can turn some of the acetyl-CoA into fatty acids that's eventually going to become lipids and stuff, and that's going to be the cell membranes. You're going to have healthy yeast making good beer for you. So if you wonder, why do I need to aerate my worts if it anaerobically or without oxygen can make ethanol? Like I said, this is one of the major reasons. So it can do that, yes.
Can you bypass this process by adding fatty acids?
I've never tried that, but that sounds nasty.
You can reduce the process by, especially dried yeast during freeze drying or drying processes, their membranes get hurt a lot. So that's why especially dried yeast need a rehydration step and then excessive oxygenation for the wort. But if you use liquid yeast, for instance, the membranes are already intact and they're quite healthy, so you can reduce the amount of oxygen that's needed.
But I've heard that you can add like a main acid, like a olive oil or something to the actual yeast that will
That's very.
propagate this process.
No, that's very interesting. I'll we have to read up about it.
Yeah, I've heard of olive oil. Yeah.
So is this what causes, you know what's with rum, the dunder thing, the ester? Is this what's happening in dunder?
It's one of the things that happen.
Everything's happening. So that's why, that's where the esters are coming from.
I can't point you to where the goat head goes into this one. Yes, you're right. It's one of the things.
That's why it doesn't smell bad. It looks bad, but it smells amazing.
Yeah, we have to know about the
Listen, guys, I'm at
dunder.
30 minutes and I'm
We're
almost
gonna add
done, so I assume I just have to. You still have to drink a lot of Rooster's Duel, so let me just quickly finish up. Sorry. So the third very important thing is it can be turned into esters. So if you've got your acetyl-CoA, these enzymes, alcohol acetyl transferases, can actually get.
Sorry, Errol. So you've created these esters, right? So can they combine to create a different flavor or different?
Give me 1 second until the next slide. But for that, like I said, the acetyl-CoA, what happens, you're fermenting, there's a lot of sugar, the cells are making a lot of this, and the cells don't want any of this to escape because you can see acetyl-CoA is cash money for the cell. So the way it kind of keeps it around is it turns it into esters. And then you get, this is also a way you can get ethyl acetate, isoamyl acetate, phenyl acetate. Basically, depending on which alcohols are around, you can get different flavor compounds through this pathway.
Sorry, can I? And then, because I've seen like with sours, so you taste too early, they're sour. You taste them right, you get your mangoes, your passion fruits, your banana. If you wait longer, what happens after this?
They get better.
So one of the things that can happen, and that answers that question as well, is something called transesterification. So if esters are hanging around, and there's acids hanging around because of sour beers, some of these acids can actually replace the acids within your esters to make new compounds. So you can, while you age your beer, that's why it's so important to age your beers. They change. They're living things. You can taste it now, 6 months, 12 months, a year. It's going to be different beers because it's a living thing. There's still yeast cells doing things. Some of these reactions occur spontaneously, so it's changing the whole time. Okay. How do we work with esters? What things can influence your esters? And this is mostly based around your acetyl-CoA fermentation temperature. If you think your cells are rapidly growing at a higher temperature, it's making a lot of that acetyl-CoA. A lot of acetyl-CoA can turn into some esters. Our oxygenation becomes important. If you think about that whole process, that entire chain I showed you, that needs oxygen. So if you don't proper oxygenate, a lot of that acetyl-CoA is not going to be able to go through the entire chain. So there's going to be a lot of spare acetyl-CoA around that can be turned into esters. Pitching rate actually changes this as well. For some reason, I can't remember the reasons now, but a lower pitch rate, for some reason the yeast go, okay, there's not a lot of yeast around, we have to make a lot of yeast, and they start propagating and eating and growing crazy. Once again, they're growing at an increased rate, they're making more acetyl-CoA, they're going to give you more esters. So I remember back when I was still trying to make the perfect vice and I wanted to get that banana ester, one of the things they recommend to you is try a lower pitch rate, try to decrease your oxygenation to kind of force this ester production into your vice. Right. That did not work. In the end, what worked was this bugger down here. We just found a better yeast that could actually make more excellent meal. So this one's very important as well. Make sure what yeast and bacteria you're putting into your beer. They do have different ways of making esters, and some of them are better at it. Just the word composition as well. Nitrogen and carbon in the words can also affect esterifications. Okay. Last thing I want to talk to you about, luckily Job talked about most of it, so I don't have to talk to you about it. It's the Philly Sour. It's a very cool thing.
Where did you get that picture from?
I've been there.
Internet.
No, it's fine.
So yeah, I'm going to go into this. Doc told you all about it. It's fantastic. I can only, what's the word, the English for this? I can only not support what he said. Yeah, anyway. So this is not my work. I blatantly stole this from the internet. It's around your questions about repitching and stuff. This guy went and he tried various different pitching rates, and what he saw was you need to stick, like Jock said, to the pitching rates. If you go above and below, it doesn't make a sour. What he did though is he was able to repitch it for 10 generations, but also, as Jock said, this guy was able to do very accurate cell counts and viability tests. So he made sure that he had the correct amount of living cells when he repitched. So if you can do that, repitch it. If not, just buy new packets. Come on. It's as easy as that. The last thing that I wanted to ask Jock about, but then he answered the question for me, is why no Sourvisiae in South Africa? So just briefly on Sourvisiae, this one is a GMO, as Jock said, so that means genetically modified organisms, so they fiddled with the DNA, and people are still kind of freaked out and scared about that. Like, if I drink this beer, am I suddenly going to make lactic acid? You're already making lactic acid. What's going to happen to you? I really want to try this yeast. If you've got some of that on the slide, I'm very tempted. But like I said, you can do both of these things. It makes ethanol and it makes lactic acid. Like I told you earlier, most yeast can make lactic acid, but they rather decide on a genetic level to make ethanol. So what did they do with this yeast? They basically, in a lab, went and they put in better genes to actually force this yeast to make the lactic acid as well. So very briefly, you can scream stop, stop, stop now. Yes. Think about a gene, if you know anything about genes and genetics, but very briefly, you need something that tells the cell to start here, read this genetic code, make an enzyme that's going to do something. Then you need the actual genetic code that's going to give you the enzyme that's going to make the sour product, that's going to make the lactate. And finally, you need something to tell it, listen, you should stop now, otherwise you're just going to keep going through all of the DNA. So what they did is they took the thing that tells it to start, and they took the one from alcohol that tells this alcohol dehydrogenase here. They took the one that tells the cell make this protein, and they made it exactly the same. So anytime this yeast, and it's a normal Saccharomyces cerevisiae apparently, they won't tell us, but it's a normal Saccharomyces cerevisiae. Anytime there's a signal for this cell to make alcohol, that same signal is going to switch on this thing, and it's going to make the protein that's going to make the lactate as well. So, and they also replace this gene with one that works better than the normal one you would find. So you've got a switch that switches it on, and it creates a machine that makes the sour better than the one that was present. Yes?
So they actually took the lactobacillus gene for LDH.
Ah, okay. Yeah.
But then used the promoter for ADH, as you say.
So it's not weird. It's a GMO, yes, but it's not weird. It makes alcohol, it makes lactic acid.
I mean, that's how we get a lot of the strains. They just spit it up.
Yes, yes. They've made Frankenvisiae, but it's fantastic.
No, patent pending. Funky myces.
Hey, we all eat beer, tomatoes,
So I'm really hoping that this would get like more traction in the world, because if it becomes okay to use this, it might open the door to play around with genetics of some other yeast in some other interesting ways, and eventually you can get yeast that do really cool things, like maybe make malva pudding without you adding them. Okay, I'm going to skip that, and thank you very much.
Not chilling. So if we're gonna have a pee break, it's gonna be very quick. We've got 3 minutes. One song. We're playing one song. If you haven't peed by then, You're missing out.
I'm supposed to see my partner.
Ja, as soon as it comes chemistry, I fucking want to fucking move. It's a chemistry thing.
It feels like varsity.
So, I tried making it sounds exactly like a lecture. And then I go to hospital.
Glad that you made it through. It's about time that somebody came
I made most of it.
Don't you feel experience?
Here comes Brucey. Woohoo!
And not so much agitation or the whole pack and a whole lot more.
Just very short. 1 year, more or less.
Yes, please. We need about 4 minutes. There you go. You've got there for glass. Sorry? I went 2 years.
Yes.
We're short of glasses, so
Yeah, no. Well, we'll share, but COVID protocol. Yeah, no,
It's just not appropriate for anyone.